Okay, let's look at another rational function and see how we can find the key characteristics to analyze it algebraically. And then hopefully with that, we'll be able to sketch an accurate graph. So first things first, what I'm going to do for myself is I'm going to try to attempt to see if the function numerator and denominator will factor. So I look at x squared minus 16 in the numerator. I know that's a difference of squares. So that will factor down to x plus 4 and x minus 4. And I look at the denominator, x squared minus 3x minus 28. I see that it's a special form of the trinomial. So I kind of look at factors of negative 28 that add to negative 3. And I do realize it does factor as well, quite nicely. So I should factor as x, let's see, 7, x plus 7, excuse me. I would say if we're going to get a negative 3x, it should be x minus 7 and an x plus 4. Let's draw that a little nicer. Okay, so I factored the numerator and denominator completely. I notice right away I can divide out the x plus 4s, and that gives me an idea, and I'll write this a little lower. This is going to tell me that there's a hole at x plus 4 equals 0. So I'll come back to that in a second, but that's something that always makes me think, write that down so you don't forget. But I do want to show that once I divide it out, I'm going to have my reduced version of my function. F of x equals x minus 4 over x minus 7. And a lot of times for a lot of the questions that we ask ourselves throughout this process, it's going to go back to this reduced function. So I'll kind of circle it to remind ourselves. Now, going back to the issue of having the hole, once we notice that we had a common factor, that is a heads up that when we find the solution to the x plus 4 equals 0, which gives us x equals negative 4, we have a hole where x value is negative 4. So if we want to find the y value, we're going to plug in negative 4 to our reduced function. So that would be negative 4 minus 4 over negative 4 minus 7, which gives us negative 8 over negative 11. And then divide out the signs. Negative over negative is positive. So we have 8 over 11. So our hole should be at, or the coordinates of the hole will be at negative 4 and positive 8 over 11. So that's something we'll want to address later. Maybe I'll write it in right now. Might save me some time. So negative 4, 8 over 11, if you want to use your calculator to approximate 8 over 11, you're going to find that it's a number that's larger than 1/2, a little larger than 1/2. And the way we try to write this, so we have negative 4, 8 over 11, we do our best to approximate it, and while indicating that we have an open circle at the hole. It's a little more exaggerative, but it's okay. So another thing I want to deal with once I've reduced my function, I also want to address, do we have any vertical asymptote? And we do. So it's a rational function. I'll label it VA. We have a vertical asymptote at x minus 7 equals 0. And if we solve, we get x equals 7. And a reminder, this is a vertical line. So we have to include the x equals part. So let's include this on our graph. X equals positive 7. Include this as a dashed line, and sometimes I'll even label it just to be clear. Okay, so we're going to take care of the asymptotes. Next thing I will go through, I'm going to deal with, maybe we have a horizontal asymptote. So I'll address this in the work labeled by HA. And in both cases, you can either look at the reduced function or the original function. And remember, when we talk about the degree of P of X versus the degree of Q of X, remember P of X is always the numerator polynomial, and Q of X is always the denominator polynomial in this situation. So if I'm comparing the degrees in either version of the function, they both appear, I'll even highlight them, the degrees are both the same in both cases. In the reduced function, the degree happens to be 1, and they're both the same. So just kind of a little note for formality. The degree of P of X equals the degree of Q of X. So this tells me there is a horizontal asymptote. And horizontal asymptotes are always horizontal lines. So this is why we have a y equals. And what we're looking for is the leading coefficient of P of X and the leading coefficient of Q of X. Well, in both cases, the leading coefficients are 1. So just so that you kind of are clear, if you're kind of setting up the ratio, we have the leading coefficient of the numerator over the leading coefficient of the denominator. And in both cases, they happen to be 1. Sometimes they're not both the same, so just be careful. We'll then just do our best, make this a little simpler. 1 over 1 is really just a 1. So now we have our horizontal asymptote, and remind ourselves it is a horizontal line. So we'll add that to our graph as well. So at y equals 1, do our best. We have a dashed line. That was a little sloppy. I'll work harder. There we go. And it's the horizontal asymptote. I'll kind of label it as well. Now at this stage, if you know you have a horizontal asymptote, you could rule out having a slant asymptote. So you could address this later. You can say, hey, there's no SA. And the reason why there's no SA, or let's say if we were asked about it, usually they would say write none, mainly because in order to have a slant asymptote, your degree of your numerator has to be 1 degree higher than your degree of your denominator. And if the degrees are the same, you don't have a slant asymptote. So we've already addressed that now, so we're good. So let's take a look. What I probably at this point would want to do for myself is find the intercepts. And so let's go through that. I'll take it off to the side like I did in the past. So if I'm looking for the intercepts, what I can do is start off with x-intercept. I go alphabetical order. This means I would set my y value equal to 0, but that means y is equal to f of x. And we can use our reduced function in this case. So again, our f of x, that's why I circled it. It's x minus 4 over x minus 7. We'll go back. If we set that equal to 0, here again, we've got a single fraction equal to 0. And when that is the case, the only possibility that could happen, this only works, a single fraction can only be 0 when the numerator is 0. So our numerator is x minus 4. So if we solve that particular equation, we get x equals positive 4. So that's going to tell us who our x-intercept is. Remember ordered pairs. X goes first, the y value is 0. So 4 comma 0, we can add that to our graph. So that's going to be right about here. And we shall do the same for the y-intercept. So for a y-intercept, you're going to set x equal to 0. So in other case, in other words, you're finding f of 0. So if you plug that into your reduced function, you have 0 minus 4 over 0 minus 7. Little simplification here. Divide out the negative signs, we have 4 over 7. So if we're going to write our ordered pair, x is 0, y is 4 over 7. And if you'd like to approximate 4 over 7 on your calculator, you can get a little more accuracy. It is a number that's slightly larger than 1/2. So 0,4/7, we'll include that on our graph, and we just do the best we can with kind of estimating where it would be. But it is hitting the y-axis. So now, at this stage, if we didn't have a calculator, a graphing calculator, we would pick a lot more values of x, plug them into our reduced function so we can see the pattern of how our rational function is behaving. But lucky for us, we have our TI. So I'm going to pull that up so that we can get an idea of our graph. Take a little time here. And let's see. Let's have you guys open the screen now. There we go. So I always like to enter my original function in, just so I can see the presence of the hole if there was one. And I'm pretty sure we have it, but I just want you to, I want to verify this with you. So again, when you enter rational functions into your function editor, the numerator is always enclosed in parentheses. So I believe it's x squared minus 16 divided by, that's the fraction bar in the sense. Open up a parenthesis. We're going to have x squared. And I believe, I'm going to check one more time, x squared minus 3x minus 28. So now what we have is our function. I'll press enter. And we can graph it. And we notice because our vertical asymptote is around x equals 7, we can kind of see that there's probably more to be desired from our standard viewing window. So in this case, I may widen out the right side of my graph. In other words, make the x max larger. So I'll play with that just to get more accuracy. So maybe with the x max, maybe I'll just make it 20. Then you kind of have a little more idea of how your function is behaving. So let's copy that over. I like to just compare it side by side. So we'll go back to our drawings. See if I can copy it onto the right, perhaps. It's a little small. Let's make it a little larger for ourselves. All right, see if I can move this a little. There we go. Okay. So you can kind of see, okay, it looks like our analyzing went well. I have a feeling I can see right away where my intercepts were. I see at +4, see that happening, and I do see the y-intercept, it's a little bit below 1. So I'm feeling pretty good. I could make a nice accurate graph here. I can sketch it. I have more points on the right side, so I will make sure I'm hugging the vertical asymptote. And before I enter a little bit further, I will just draw the left side for now. And then I'll do my best, continue on the right side and kind of think that your function has a hole. And the way I see it, it does not appear to cross its horizontal asymptote, but it's really hard to tell by looking at the TI. So before I kind of make a final decision on my graph, like is this part of the graph or even the far edges, like we don't know what's happening way to the right as well. Will it ever cross our horizontal asymptote? And so you could kind of take some experimentation. You can say, well, let's check our TI. Let's see if it gives us any information on this one. So I go back. And then I kind of say, well, if I want to see if it crosses my horizontal asymptote, maybe I should graph my horizontal asymptote. Kind of hard to see if it's not there. So you'll notice what I did. I scrolled all the way over to the left side of my function editor, and I press enter. And I think I have a TI-84C uploaded for you guys to see, but if this were a TI-83 or just a TI-84 without color, you would end up pressing enter multiple times and you can figure out how to get a dashed line if you want to be fancy, but you don't really have to. It's just try to interpret it. I played around with the TI-84C. If you press enter, it allows you to change your color. It allows you to change the shape of your line as well. So I just made a dashed line. I pressed OK. And then I have to scroll back over with the arrow key. I'll type in my horizontal asymptote and I'll graph it. And you see, OK. So you do see this horizontal asymptote a little nicer. And if you had just a solid line, it doesn't matter. And at this point, when I'm looking at it, you know, it looks like it's barely touching it, if not at all. You want to take it a little bit higher in terms of looking at the far edges of the graph. Sometimes we call it like endpoint behavior of rational functions. So maybe we take a little bit larger, a wider window. So maybe x min negative 50, maybe x max 50. And just kind of inspect what's happening here. And you can kind of see, well, it could be tricky because we don't know if it's because the function itself in blue, if because it's graphed in a bold line versus the thin line that the horizontal asymptote is graphed in, we can't tell if the graph is actually crossing. You can keep taking wider values, but it kind of is inconclusive if you're just trying to know by just viewing it. So there's a few things you can do to inspect. You could try a lot of values of x and see if your y values ever become higher than 1, because I'm trying to look at the left side. It's a little nicer for me to try to interpret. So I could play around there. We could use the trace button in that sense. And I'll kind of show you like at x equals, what did we say? Like x equals, I'll say x equals 6, just so that you guys can see. You'll notice at x equals 6, it shows you the corresponding y value and where it's located. But if we keep playing, let's go like x equals negative 1. Gives you a corresponding y value. Even when you press where the hole is, this is why I like this part. When you press x equals negative 4, you notice, there's no y value, and that's correct because that's where the hole is. But keep pressing numbers to the left of negative 4, like negative 10. And notice what type of y value you get. It looks like we have 0.8, so that's still smaller than 1. We're not crossing that yet. Let's pick negative 30. And we notice, well, we are getting closer to 1, but it looks like we're still in good shape. We're still below 1. So let's pick again, like negative 46. And we can even go further and say negative 100. And it appears it keeps getting closer and closer. So maybe if we tried a lot of values around like negative 100, negative 1000, we can then determine, does it really cross or doesn't? So that's one way to help you figure it out. But sometimes we don't have the time for this, or maybe our TI is not available to us. So when that is the case, we have one more trick that we can pull out from our tool kit. I'm going to go back and show you analytically to really determine, do you have a hole or not? So let's go back one more. I shouldn't say hole. I meant, do we have our function crossing the horizontal asymptote? We already know we have a hole at negative 4. That's about right here, just in case you guys are looking through that. And I'll highlight that again, just in case. Okay, so one last question for us. Does our graph ever cross its horizontal asymptote, and the horizontal asymptote is y equals 1? And the way to figure this out without needing a calculator or just guessing 50-50 chance it does and doesn't, we told you that you can set your reduced function, if it's reducible, or just set your function, set it equal to the value of the HA. So in our case, the value of the HA was 1. And then see what happens. So for instance, what was that? X minus, I'll double check one more time, x minus 4 over x minus 7. Now, if we try to solve this equation, and I'll move it over just so that we have a little more room to discuss this. Here we go. If we try to solve this equation for ourselves, you can say, okay, a little bit of review on being a rational equation. We can multiply both sides by the LCD x minus 7. So then on the left side, the x minus 7's divide out, and you get x minus 4 equals 1 times x minus 7. And then when you try to solve this and you're saying, okay, I know it's a linear equation, let's just move all the x's to the left. So if we subtract x on one side, and then I move the constant to the other side, I add 4 to each side. Guess what happens? Look at this. We get the x's completely canceling out, as well as the 4s. So we get 0 on the left-hand side. And on the right-hand side, we get ourselves, what do we have, -3. And so right away, we got ourselves what we call the contradiction, which means we have no solution to this equation. If this is the case and you get yourself a contradiction, that means your answer to, does f of x ever cross its horizontal asymptote? Your answer is no. So that you have further analyzed this and you're really clear about what they call end behavior or endpoint behavior. And later on in some of your future math classes, you'll call it behavior in the long run. It might be very interesting to understand, whether it crosses its horizontal asymptote or not. So hopefully all of these items will help you graph an accurate graph. And of course, we're going to use our TI in this course to help us further have some accuracy. It helps out a lot. I'll see you in the next example.